Hi and welcome to this edition of Engineers Gone Wild. Today we'll be joining a team at the University of Manchester who are creating a context-responsive freezer.
Hello, this is the freezer that we're going to be using here. It's quite a standard freezer. What we're doing is optimising the freezer to reduce energy usage. So Shan will be talking about an optimisation algorithm that was done to reduce the cost of the freezer. Devin's going to be talking about the communications, and Christos will be talking about the temperature sensing aspect of the project, and Jamie, who you've already seen, will be talking about the e-box, which is a device that will sit in the home and allow you to control the freezer and any other appliances attached to it.
Okay, so my name's Jamie. You saw me at the start of this video introducing the project. Basically, my role for this project has been to create the central control system known as the e-box. This is where the optimization algorithm that my colleague Shantanu talked about earlier will be processed and run. And to do this, basically what we're going to be using is this embedded board here, if Clayton shows this. It's got two main functions. We've got appliance control here and appliance statistics. Starting with appliance control, this is where all the control of the hardware will be carried out. So if we add the freezer to the system, we can see the events for a given plan are populated here. These are the turn on and turn off events for the freezer for the day. So at these times, this is how the plan would be executed. This display just allows the user to gain sort of an understanding of what's going on within the system. And to make it more clear, we have the appliance statistics. This is a graph that shows electricity consumption and the electricity cost. So for that plan we just generated, here we see a variation in appliance power consumption over the time period, and to enable these to further understand how this saves them money, here we have a graph of the cost. As you can see, where we have low power consumption, we have a high cost, corresponding peaks and troughs here, and then again here where we have a peak and a trough, a peak and a trough. Just to make it a bit more clear exactly what the electric prices are. Here we can see the graph of the price on its own.
So the aim of our project is to create the context-responsive freezer. Context being an increase in energy efficiency and also a reduction in price for the end user. At present, there are two energy pricing schemes which are day and night. It's thought that in the future there will be more renewable energy on the grid, so that there will be a much larger range of energy pricing. Our freezer aims to take advantage of times when electricity is cheap to boost the cooling in the freezer to act as an energy store. So when the electricity is expensive, we're able to turn the freezer off and allow the temperature to rise, thus saving energy. And this project is a year-long project, and we'll now move on to other members of the team who will talk to you in detail about the other aspects of the project.
Hi, I'm Shan, and I'll be doing the cost optimization algorithm for this project. Now, what you got to understand is a typical freezer like this one, Beko, or that one, basically is designed to operate at a flat rate. You know, one single price for the entire day. So what does it do? It uses a thermostat control to simply oscillate between two temperatures, say minus 18 and minus 22 for instance. Now what we're trying to do is design the freezer operation for a dynamic pricing system where every hour would have its own rate. Which means that you would use the freezer more during the cheaper hours and less during the more expensive hours. Important thing to understand is that you've also got these temperature constraints. You cannot exceed the freezer temperature beyond a certain point, and you cannot lower it below a certain point either. And that's what my cost optimization takes care of. So based on the constraints and the different rates for every hour, it calculates what the on time in a given hour should be. So now if I compile this, for instance, you will see compile and run. You can see, I don't know if you can see clearly here, but every hour's got a different rate, a different on time I mean. You know, the first hour's for instance got 0.713, the last hour's got 0.604. They all have different on times because the more expensive hours are using less on time and the cheaper hours are using more on time. Now you might be confused a bit as to why the most expensive hour is in zero. It's because you've got to take care of those temperature constraints I talked about earlier. So yeah, that's about it.
Hi, I'm Bevan. I'm going to talk to you about the communication system we'll be implementing in this project. we'll be implementing a wireless communication system using the MiWi protocol. Over here we have a wireless adapter which will connect to our e-box. From this adapter we will transmit commands to devices connected to the system, such as the freezer or a washing machine and so on. Over here we have the circuit board that we will use to control the operation of the freezer, and attached to it we have another wireless adapter to send and receive data. At the moment we have currently established a point-to-point link between these two devices, and at the moment we are currently trying to introduce a third device into the network.
Hi, I'm Craig and I'm responsible for the hardware on the project. There's two bits of hardware that we designed. The first one is a voltage and frequency circuit. Now the reason we're measuring the frequency is what we want our freezer to do is we want it to cut out if the frequency goes outside the allowed limits. So effectively we're going to build in a load shedding device. Basically what we're doing here, we want to measure the frequency of supply. So taking this circuit here, it's this voltage transformer, and it feeds it through a series of op-amps and produces this square wave. Now this square wave you can see on the oscilloscope, if you look at the frequency, it's at 49.92 Hertz at the moment, so it's within the allowed frequency ranges. So basically what we're going to do is we're going to be monitoring this, and I would like to show you on the Omicron how if I change the frequency it changes on here and changes to a wider square wave, for example, but the Omicron isn't working at the moment. So you just have to take my word for it that it does actually work, and if I was to change the frequency supply it would change on here. The next piece I want to show you is this current transformer circuit here. Now the current transformer circuit is we basically built a smart meter. So we've taken the existing smart meters that you can buy nowadays, such as ones like this, which you clip around your meter tails at home, and we've basically built our own version. So you're going to have to imagine that this here is the meter tails coming up on meter at home. So I'm going to clamp that round like that and switch on high current device, something like a kettle, and you can see we get this reading on the screen. Just to prove that is actually coming off the kettle, if I take that off there. Okay. And then, for example, if you switch on something else like a light, the maximum voltage goes up slightly. I mean, something like a light that's only 60 watts is going to make a big difference. But something like this kettle, which is around 9 amps, makes quite a big difference. And if I look on this graph here, I can read the display on there. It's giving me 450 millivolts. So if I go follow the graph, 450 millivolts, it's about just over 9 amps. So by measuring the voltage output from effectively this current clamp and current transformer circuit, I'll be able to measure pretty much any current that flows in your house and therefore know the power, which will then be outputted to our e-box screen. So Christos, what are you doing?
I'm preparing to test the chest freezer and compare the results with the test performed on this freezer. Hello, my name is Christos Mamidis. I'm here to talk to you about temperature measurements for the project. The first thing I did is do some tests, take temperature measurements of the freezer under different conditions like half load, full load, opening the door, see what effect this has. These are like some results shown under open door, like here it's when the door is open, then close to reach the minimum temperature, then again open, but open door test, but the compressor was off, and again let it drop to the minimum temperature again by closing the door and opening the compressor. Also tests have been done on this chest freezer to show what effect has being a chest freezer so that the cold stays in when the door is open, and also this freezer has much better insulation. Also this circuit has been built to connect to the RTD here and get an output voltage from here to be input to the ADC converter of the microcontroller, so that the microcontroller would be responsible for temperature measurements on the final thing. That's it.